So we've now built up these 5 molecular orbitals, and we've looked at their symmetries. What we're going to do now is, because we want to now look at the molecular orbital interaction in ferrocene from a molecular orbital point of view to really understand how the CP is interacting with the metal, which you simply cannot do with valence bond theory or all these other Mickey Mouse theories. You have to turn to molecular orbital theory. And here it is. Now, that's one CP ring. Now let's put two of them together. Ooh. Now what I'm doing here is I'm building up the molecular orbitals of the cyclopentadienes that are going to then ultimately interact with a metal. Now, all I'm doing, first just one note here. I've deliberately chosen that these rings are facing in opposite directions. It doesn't have to be that way. You can employ the same arguments if they're eclipsed. I'm doing this because it's just a little bit easier for the next step, the step that comes after this. So what am I doing? I'm taking these 5 molecular orbitals here and I'm combining them with each other. I'm combining them with each other. Now let's look at the first orbital here, this one. Now, how can I combine 2 of those together? I can combine 2 of them both pointing in the same direction, the phases. In other words, phi 1 plus phi 1. Or I can combine them in a way that they're pointing in opposite directions, phi 1 minus phi 1. I'm talking about the phases. In other words, I can have 2 combinations, 2 ways of putting 2 of these together. And that's what they look like. And the symmetry label, so what these labels here, they're Mulliken symmetry labels, tells us about the symmetry of that molecular orbital. So what we're actually doing is we're building up the molecular orbitals for one CP ring, and then using that, we're building up the molecular orbitals for 2 CP rings. All right. So if we put 2 CP rings together, I can have 2. In this case, it's phi 1 minus phi 1. Look, the phases are different. Do you see that? Here it's phi 1, or let's say phi 1 plus phi 1. The phases are the same. So there's 2 possibilities, and they happen to have a symmetry called A1G and A2U. Now, A and these are Mulliken symmetry labels. Everything means something. But for me, you don't really have to know exactly what it is. What's important is this G and this U. What does that mean? Yeah, what does that mean? Correct. In other words, if I have an inversion center in the center here, if I go through that inversion center, what do I get? Well, there's the inversion center. Let's say I start at the top there. Go through the inversion center. Let's say that's a plus. Through the inversion center, plus. So it's gerade. Here the sign changes from plus, or let's say minus, to plus, ungerade. All right. So, and basically what you have, the 2 and the 1 is associated with degeneracy and stuff like that. It's not so important because we're going to do this now in a pictorial way. So that's the situation for the sigma. So for the sigma CPs, if we put 2 together, we can have 2 of them. 2 of them. Now, let's talk about the situation for pi. Now we're starting off with 2. So we've got to consider all the combinations of those 2. So how many are we going to end up with? 4. 1, 2, 3, 4. Now notice what I've done, exactly what I've done at the bottom. Phi 1, basically putting the 2 together with the same phases pointing in the same direction. Or putting the 2 together with the phases pointing in opposite directions. Same, opposite and, no, sorry? Yeah. Put all the combinations together, up and down, up and down. So we get 4. And we do play the same game for the delta symmetric orbitals, and we end up again with 4 possibilities. Those are the symmetry labels associated with all the orbitals. All right, these are gerade, these are ungerade. Gerade, ungerade. Now, we've built up the molecular orbitals from first principles of the cyclopentadienes. Now what's the next step?
Put the iron on the machine.
Yes. We've now got to play a game of mix and match. We've got to take the d orbitals, the s orbitals, and all the orbitals at the iron, of course there's 9 of them, 3p, 1s, and 5d, look at their symmetries individually and try and mix and match it with these orbitals that we've built up here in terms of their phases and symmetries, and see which goes with which. And then we can build up the molecular orbital diagram. That's how we do it. It's very simple. Now, let's do that. Let's in fact do that together. So let's start off with the sigma symmetric orbitals. All right. Well, there's already the solution basically. So we can think, if we look at these at the phase here of this molecular orbital, notice that the negative phase of these p orbitals is both pointing in towards the metal, which would be sitting there. Now, which orbitals match that? Well, an s orbital, because an s orbital would have the same phases, and a dz squared orbital would match that as well, wouldn't it? Because look, the phases match. Black, 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 and black. Black is back. So those match. So that's a symmetry match. Now, in fact, more formally, if you look at the symmetry label associated with an S and a dz squared orbital, you'll find that the symmetry label is the same as this A1G. And that's why they match, formally, from a group theoretic perspective. But you can see that they match visually. So we're doing a visual matching. Now let's play the same game with this orbital. Now remember, we built this one on phi1 minus phi1 with opposite, here they're both pointing in the same direction. Up and up, or let's say minus at the top. Now which orbital is going to fit with that one? Remember the metal's sitting in the middle here. PZ. PZ. Because there's white at the top, black at the bottom. So a PZ has white at the top, black at the bottom. Fits. Do you see how we mix and match the orbitals? Now, does everyone follow so far? Is everyone absolutely following? Elena?
Well, I understand what you understand.
All right, that doesn't sound very encouraging. That's I'm going to take your word for it. It's mixing and matching. All right, now let's play the same game with the dz squared, with a pi symmetric orbital. Right, now before we get there, let's try and figure out which, let's try and predict. So let's start off with this orbital here. All right, actually it's possibly easier to look at it from this perspective. Now, if I want to put an orbital in there, which orbital is going to have the appropriate symmetry there? A d orbital. A d orbital. Some d orbital will fit in there because remember, d orbitals look like this. Right? So if you look at this and how this is shaded, right? We've got white, white, black, black. And that's what we have there. So if I put a d orbital in there, one of the d orbitals should fit. Now here we've got black, well, maybe we can find something there. So you see, this is sort of the mental game that you're playing. You're looking at the orbital, you're looking at its phases, and you're trying to put it in with the orbital that has this, with a molecular orbital that you've built up that has the same phases. It's kind of like that game you played when you were a child. I don't know if you had it in the 80s. We had it, but it's like this big cube. Well, it's actually like a dodecahedron. Like it's got many surfaces with little shapes cut in it, like a triangle, a square, a circle, and then you have all these blocks that you've got to put through there. Right, and a circle only goes through a circle, or a sphere only goes through a sphere, and then you have a star, and I had a triangle, and all these things. I loved it. It was one of my favorite toys. Now that's basically what we're doing here. We're trying to match shapes up. Right? What we're actually doing is we're matching symmetries. So let's just look at the results. As I said, look there, check it out. That YZ orbital, because remember we're using a predefined coordinate system here, a predefined coordinate system, that baby is going to be perfect. Look at that, it's got a white pointing up diagonally, as we have there, and blacks pointing there. So it's a perfect symmetry match, it fits. What about this one? Now it's a little bit more difficult to visualize this, but this orbital matches in there. And if we look at the bottom here, this p orbital matches perfectly the symmetry of this molecular orbital, and this p orbital matches the symmetry of this orbital visually. But also from a group theoretic perspective, they have the same symmetry labels as these orbitals, and you have to match the symmetries in building up a molecular orbital diagram. I'm doing it visually now, but you can also do it analytically using group theory. Right, so it's fun, right? It's really exciting. We're building it up ourselves. How cool is that? Don't look so depressed. It's exciting. It's exciting. Now let's deal with the delta orbitals, of which we have 4. Now it turns out that the E2U delta orbitals do not have any orbitals of appropriate symmetry on the metal. So those we can't match them with anything, but these, for example, can be matched up with a dxy and a dx squared minus y squared. And if you look at the phases and form of these orbitals here, you'll see that they match the phases and forms of the molecular orbitals that we've built up of delta symmetry. With a bit of mental gymnastics, but you can see that. So what we've actually done is we've laid the groundwork for the molecular orbital diagram. We've matched we first of all derived all the symmetries of the CPs, the 2 CPs, and now we're going to, and we've matched them with all the available d orbitals, p orbitals, and s orbitals coming from the metal, and we've done that visually, and now we can put everything together. We can put everything together in a molecular orbital diagram, and that's what we get. Now, let's do this in a stepwise fashion. Let's do this in a stepwise fashion. All right. Here we go. Now, don't freak out. This is from the University of Basel.
Is it so right as a notes?
No, I wouldn't recommend. I'd rather just pay attention because I'm going to post all of it. Now, let's just go back. Right. Now, all we're doing is we're taking all that mixing and matching game we just played, and we're just putting it on an energy diagram. Now, what do we have here? We have we have in total the 10 orbitals that we derived at the beginning of this game, right? Starting from this. That's where we started. From that, we derived those. Sigma, pi, delta. And what we have here are simply all the metal orbitals. N-1, D, S, and P. Very simple. They all have symmetries associated with them, and we've just done that ourselves by mixing and matching symmetries. And what we're doing here is we're doing the same thing in terms of an energy diagram. So let's see what happens step for step.
I have a question, maybe it's a stupid question, but the d orbitals are lower, like it's one energy lower.
Yes. Yes, why is that? Well, it's because in complexes, the d orbitals go down. I mean, if you look at the Aufbau diagram of a free metal, of course it's different. The s and the p come first. Mm-hmm. But in a metal complex, the d is lower in energy. Okay. It's lower in energy. And the reason for that is, what the atom does is it promotes the electrons into the d orbital so that they're available for bonding, and so the energy goes down. That's very important. So in fact, in any molecular orbital diagram of a complex, it's always n-1 d ns np for the metal. That's the order of the orbitals energetically if you're building up a molecular orbital diagram, and then you have the ligands. Right? And that's how it works. Right. So now what we're doing is we're matching symmetries with symmetries, which we've already done. We've actually already done that. Now we're just doing it in a different format. So what are we doing here? We're taking the A1G orbital, so this one, and we're matching it up with an A1G orbital. Now you can actually go back to the pictorial matching to guide you on your way. So it's a bit of a difficult thing that we're doing here in the first step, but we're combining this orbital with one of these, right, of A1G symmetry, which is in fact, the thing is there's in fact two of them. You see, because remember in that very first, in fact, let's just go back there. Don't get your knickers in it first. Remember that for this one there were in fact two orbitals that matched, the s and the dz squared. Those two have A1G symmetry. And here you can see it pictorially. So in the molecular orbital diagram, obviously, this one of A1G symmetry is going to match up with that one and with that one. So in fact, there's three orbitals that are interacting in this interaction, and here they are. There's the first interaction, so this is the interaction between this one and the dz squared orbital. These are all degenerates, right? So that's that one there, this one. And now look what happens, there's a bit of, that s orbital is going to come along and it's also going to involve itself. Now there's three orbitals. So in fact what happens is very interesting, is you have a bonding, an anti-bonding, and a sort of a non-bonding interaction. Because remember, if you're building up molecular orbitals, for every atomic orbital that you put into the mix, there must be a molecular orbital. Now we put three into the mix, this one, and this one. So the result is there must be three molecular orbitals. One is bonding, one is anti-bonding, and one is sort of non-bonding. And that's why we have these three lines. So these are interacting, boom, boom, boom. Right, now let's see what, let's play the movie forward. What's happening there? Well, all that's happened there is actually that we've just basically, this is this three orbital interaction. Nothing has really changed. We've just adjusted the energy slightly. Doesn't mean too much. All right. Now, what's going on there?
The one with the
Yes. I'm now looking at this orbital here. Let's go to the picture. Let's go to the picture. There it is. We found in our game of mixing and matching that there was only one orbital that corresponded in symmetry with that one. It was the pz orbital. There we see it clearly, visually. Now remember, I'm using this coordinate system. And now, if we look at our diagram, that's exactly what I'm doing here. So I have, this one is corresponding with a pz orbital. Symmetry is U, look at that. So they can form an interaction. It was this orbital here, and we have this interaction. Now there's two orbitals participating in this interaction, so it's going to build two molecular orbitals. This one, which is very low lying, will be bonding, and an extremely high lying anti-bonding sigma star orbital. Now let's play the movie forward. Next interaction, what's that? So, now I've dealt with all the possibilities with the sigma symmetric orbitals, now moving up to pi.
So those would be two
Yes.
Yeah,
Yes. Yes. So, all I'm doing here is I'm building up the interactions. Let's go and have a look at it pictorially. I don't want you guys to lose it. That's what we're doing. That's what we're doing. We're basically mixing and matching. And we see that each molecular orbital has an associated metal-centered orbital. So, if I go to the diagram, that's let's just go back one step. Oops. Right? There we go. And now, there's the next one. So you see, we saw just now pictorially that each of these have one orbital associated with them. So we're going to have a total of how many in total? Molecular orbitals. 8. 1, 2, 3, 4, plus the metal orbital of the appropriate symmetry, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Now that's quite easy. These are pi symmetric. So it's, you can think of this as a sort of a pi star, and this is also a pi star. And of course, this is higher in energy, this one here, because it's interacting with the p orbital, which is higher in energy, and that pulls the energy up. Do you see that? Whereas these are interacting with d orbitals. Look at that, the lines coming from a d orbital, which are lower in energy. So the energy of the anti-bonding orbital is not as high. It's all relative, right? So now let's play the movie forward. Now we've dealt with these orbitals. Now we're going to look at those. That's it.
Oh, okay.
So remember, we found in our game of mixing and matching that there were no orbitals on the metal of appropriate symmetry to go with those, unfortunately. So we only have 4. 1, 2, 3, 4. Let's go back to our diagram just to make sure, pictorially. Yes. 1, 2, 3, 4. And there they are. 2 bonding, 2 anti-bonding. Now this is very interesting. You see what's happening here is that these are high in energy, kind of high in energy, and these are low in energy, so it's putting the energies down. Do you see that? So you've always got to take the energy of the orbital on the left and the energy of the orbital on the right into consideration, and they sort of scale each other. Do you see that? And that's how we build up a molecular orbital diagram. Isn't that rewarding? This isn't some Mickey Mouse valence bond theory or Lewis structure. This is reality. This is the closest you're going to get to reality in understanding the bonding. Now let's look at it a little bit more closely. How many electrons are there in ferrocene? 18. We've built up our beautiful molecular orbital diagram, and now let's put the electrons in. Oh yes. What are those two there? Let me go back. What's that?
Are the two that don't have a orbital?
Exactly. They don't have so they stay on the same energy because they're not mixing with anything because there's nothing of appropriate symmetry. All right. Now let's put the 18 electrons in. There they are. Now there is this notion in molecular orbital theory of the highest energy occupied molecular orbital and the lowest energy occupied molecular orbital, HOMO and LUMO. So, what is the HOMO here? Yes. And what is the LUMO? Yes. Yes. HOMO and LUMO. Now, HOMO and LUMOs are important because they tell a scientist it gives the scientist a tool to predict reactivity. It tells the scientist what sort of things will react with this molecule. That's why you always turn to molecular orbital theory in chemistry, if you're a scientist. So, and now let's look at another consequence. Let's now look at the nature of the bonding interaction between the cyclopentadienes and the metal very carefully. Check it out. It is a sigma and pi donor and a delta acceptor. Look at that. Because look carefully at the electron distribution here. This is coming from the CPs, and that's the delta orbitals. They derive from delta symmetric CPs. So these CPs, molecular orbitals, are forming molecular orbitals with a metal. So it's a sigma and a pi donor. But look at these delta symmetric orbitals. What are they doing? They are forming it, they are empty. They are empty, they have nothing to give. But they are picking up electrons here from the metal and forming a molecular orbital. So that in a way, you can think of these as being, as the CP as being a sigma and pi donor and a delta acceptor. Those are that is the bonding nature of a cyclopentadiene in ferrocene. Now, this molecular orbital diagram is not just for ferrocene, it holds for all metallocenes, homoleptic metallocenes with D5D symmetry, because that after all is the symmetry. If I build it up in this eclipsed configuration here, with the two CP rings sort of staggered relative to each other, sorry, that's not eclipsed, that's staggered. Or they're sort of opposite each other. I could have played the same game with the eclipsed conformer. So that is the short and long of it. Now let's return to the PowerPoint presentation. Sorry. And let us proceed. All right. So there you can see clearly the HOMO and the LUMO. The LUMO is antibonding, the HOMO is well, it's bonding. And that also explains why. Do you see now why ferrocene is so stable? Because the HOMO is populating a bonding orbital.
Why is the bonding?
Well, it's actually not really bonding, it's sort of non-bonding. Remember, this was the orbital that was formed in that, right at the beginning when we were building it up from that weird that trio of orbitals that interacted. Remember? I think it's the dz squared, the s, and this orbital here. They interacted. And so it's not really bonding, it's actually sort of, you're right, it's sort of non-bonding. Yeah. But it's certainly not anti-bonding. That's the important point, and that's another reason why ferrocene is so stable. Now, let us suppose I were to reduce ferrocene and pump in another 2 electrons. Tell me about the stability of the emerging compound. Sorry? Yes, in other words, if I were to make Cp2Fe 2 minus, for argument's sake, it would become more unstable. Why? Because I'd be populating antibonding orbitals. Now, here we have a series of metallocenes, all of which basically obey this molecular orbital diagram that we've derived here for all these metals. And this is the associated electron configuration. Now notice, ferrocene is sort of sitting here. That's very stable. But because of this molecular orbital diagram, it's even possible to have 20 valence electrons. This is nickel-OC, Cp2 nickel. It's got 20 valence electrons. It exists. It's reactive, but you can isolate it. And it's in this case basically got an extra 2 electrons. If you distribute 20 valence electrons into this thing we've just derived here, you're going to pump in an extra 2 electrons there, And of course, it's going to be more reactive than ferrocene, but you can apparently isolate it. So let's look at some other examples. We have these early transition metal. Let's forget about CP2 titanium because it turns out that that actually doesn't exist as a monomer. That's a sort of a special case. But vanadocene and all its different oxidation states, chromocene, these are very reactive and air sensitive. And the reason is not because we're populating the antibonding orbital. The reactivity there is driven by the fact that if you look at the electron configuration, a simple way of understanding it is that there's lots of unpaired electrons. So it tends to be more reactive. But the moment we populate antibonding orbitals, for example, here CP2, this is not magnesium, manganosine. We've got 2 electrons in the antibonding orbital. It's going to be certainly more reactive than ferrocene, and so on. CP2 nickel plus is going to be more stable than CP2 nickel because I've depopulated the antibonding orbital. It's also possible to make, here we have ferrocinium, so CP2 ion plus we call ferrocinium. It's also stable because all I've done is just depopulated this orbital here, which is a pretty innocent orbital anyway. It's not doing anything really. Now, the HOMO orbital, the LUMO orbital here, as you can see, is antibonding in nature. And basically, yeah, that's sort of the way to think about this. Now, you can build up molecular orbital diagrams also of bent metallocenes. Basically, what's going to happen there is you're just going to distort the energies. We're not going to do that. But following similar reasoning and rationale, it's possible to build it up for the bent case as well. So, are there any questions? Yes?
If you were to oxidize ferrocene to up to 2+, would that make any difference in stability considering you're just...
Well, it is 2+.
Right.
Remember, ferrocene is oxidation state 2+.
Oh,
formally.
I don't
Okay.
think it means like charge.
Yeah.
In other words, if you were to take another electron out, well, that's what we've done here, actually. This is ferrocinium, is CP2. This is ferrocene minus an electron. So you're just taking one electron out of that orbital. This is the electron configuration for ferrocene, ion 2+, formally. But this electron has been, one of these electrons has been taken out. And that's why it's CP2 Fe+. It's open shell, it's paramagnetic because there's one unpaired electron in there, but it's stable.
So if you do it, again, it would make a difference because you're just interacting with the non-bonding.
Exactly.
Okay.
Well, it's essentially non-bonding. I mean, it's a little bit bonding. It's a little bit bonding because, you know, it's this weird three-centered interaction. Now, another very interesting fact, before I forget, is this notion of formal and real oxidation state. All right. Now, formal oxidation state is when we look at the molecule and, like we say, ion is +2 because it's got 2 anionic ligands. Now, nature doesn't like that. You know, nature, it doesn't work in ones and zeros. It doesn't work in binary. So that's the formal. We call that the formal oxidation state. But you can measure oxidation states spectroscopically, and then you get sort of the real oxidation state. And techniques that we use for that are techniques such as certain X-ray techniques, X-ray emission techniques, XFs, and so on. And if you measure the real oxidation state of iron, will it be more or less than +2?
Depends on the electronegativity.
It doesn't depend on the electronegativity, it depends on this. Remember, I said that a CP is a sigma donor, a pi donor, and delta acceptor. So what does that mean? What's it doing? If it's a delta acceptor, look at the MO diagram. Yes. It's sucking electrons. You can think of it as, let's draw it. It is a delta acceptor, so that is going to subtly change the oxidation, the measurable oxidation state of the ion. And do you again appreciate that the only way you can rationalize that is by looking at molecular orbital theory? There's really no other way to understand it. So going forward in your chemical studies,
I don't get how you from that drawing can see that it's less than 2.
that it's what?
The oxidation state is less than 2 based on that.
Well, okay. This was just to show the interaction between the CP and the ion. I'm basing that on this diagram here. It's a delta accept. The reason why overall the CP is basically sucking electrons away from the ion is because look again at the orbital interaction. Those delta orbitals, which are interacting with the metal orbitals on the ion, are not contributing anything to the bond. Look at that, there's nothing there. But it's forming nevertheless a molecular orbital with with metals on the ion. And so those electrons are coming from the metal, but they're being shared in a molecular orbital with a CP of delta symmetry. Whereas the pi and the sigma symmetric orbitals, these are populated. So although they're donating electrons to the metal, it's an equal partnership. Do you see that? Look at the diagram.
Yeah, I get that.
It's an equal partnership. And here it's not an equal
I don't
partnership.
understand why the oxidation state is less than 2 plus.
Because if you have no.
Because it's a delta acceptor. Because here it's an equal partnership. Here, this is not contributing to the equal partnership. So you can think of these molecular orbitals that are built up from these delta symmetric orbitals basically sucking electrons away from the ion, and that effectively reduces the oxidation state.
So where did that increase it?
No,
because
because
you're
It's
the
putting
electrons
it away more now, does it become more fun?
No, because the electrons come from the CP and you put them on the ion.
No, she's right.
Yeah?
You're right. You're right.
What?
You're very sharp, Julia. That's right. The delta, it's a delta acceptor. So overall, the net effect is that it's pulling electrons away from the ion, which means the electron density is getting less, which means it's actually, in a way, being oxidized. So actually, you're right. So the actual redox state will increase to, let's say, 2.5.
Then I don't get it anymore.
No,
Like, it made sense before and now it doesn't make
All
sense
right.
anymore.
There's also sigma and pi donor.
Yes.
So it's giving electrons and taking electrons away. It just depends how many.
Well, the thing is, all right. Everyone calm down. Let's start at the beginning. Look at what's happening here. These are the sigma, these are the pi, and these are the delta orbitals. These are contributing to a partnership with a metal.
Yeah.
These are contributing to a partnership with a metal, an equal partnership. Because we've got 6 there and we've got 6 there. It's a D6 metal. So all the orbitals that we build up from these and these, it's an equal partnership. The net effect is that it's not going to change the oxidation state of the metal. Now, I now take the delta symmetric orbital, and there, this guy, he's not contributing anything to the partnership. So the net effect is that this molecular orbital, right, which is built up from these orbitals here, these delta symmetric orbitals and whatever, and these orbitals here, right, or whatever, yeah, they were these, actually it was built up with orbitals here. Look, there and there. See there? There. So it's built up from these d orbitals. So that is the molecular orbital. Look closely. Built up from these delta symmetric orbitals and these metal orbitals. However, these 4 electrons come from the metal. CPs are not contributing to the partnership, which means overall, because this is a molecular orbital is going to be somewhere between the metal and the CP ring, remember? It's not just localized on the metal anymore, it's localized over the molecule. And so, the net effect is that it's a delta acceptor, and that the effect is, if you will, that it increases the oxidation state because it's effectively, in a way, kind of oxidizing the ion. So Julia, you're right, thank you very much. Everyone give Julia a hand. That's true, that's true. In fact, this is one of the questions we used to ask master students in an oral exam, right?
Yeah.
It was the first question we used to ask them. Explain to us why the oxidation state in iron, when you measure it, is higher than 2. And that was the explanation, right? So, you can answer the first question on an oral exam for advanced inorganic chemistry at master's level already. Now, so that's the molecular orbital considerations done. Now, the last thing that I want to discuss in the last couple of minutes, which is sort of a bit of a lighter theme, is this notion of reactivity. Now I'm going to restrict my discussion here to the reactivity of ferrocene, because it exhibits very interesting reactivity. As a matter of fact, the reactivity associated with ferrocene very closely matches the reactivity associated with benzene. Now why is that? Why is that, guys? Yes, because it's aromatic. So I just want to write down one beautiful example to illustrate that. This used to be a practical at the University of Cape Town second year. And ferrocene is nice because you can do nice air-stable chemistry generally. If I react this with an acid chloride, what is the result going to be? You've all done the Friedel-Crafts acylation and alkylation reactions in organic chemistry, I assume. Yes. All right, so not everyone's done the advanced organic. Actually, yes. Well, you have something in organic chemistry where you can basically, it's called Friedel-Crafts acylation. And what you basically do in organic chemistry is you take benzene, you react it with the Lewis, well, in the presence of catalytic amounts of a Lewis acid, and an acid chloride, for example, CH3COCl. And what you basically get out of that is a substitution. That's Friedel-Crafts acylation, very important reaction in organic chemistry. Now we can do the same thing with ferrocene, it turns out, and we end up with very interesting, in fact, 2 products. What will the other product be? No. The problem with if you do this reaction with ferrocene is...
the carbonyl and aluminate?
Well, you're thinking, I like the fact that you guys are starting to think about reactivity. I love that. But no, it's actually much simpler than that. You have a problem with selectivity when you do these reactions with ferrocene, always. That's a problem with this. It behaves in an aromatic fashion, but you actually end up with a mixture. It's difficult to control these reactions, but you end up with a mono and a di substituted version of the acyl. So there's an issue associated with a selectivity.
Would there also be like unreacted interface?
Yes, of course, the stoichiometry doesn't fit, but of course there would be, to match stoichiometry, yes. there would be unreacted starting material. It's not going to necessarily go exactly in a 1-to-1 ratio, but there's going to be a mixture of mono and di substituted. All right. Now, that's sort of a classic example highlighting this beautiful trend. Now, another, I think, very interesting reaction associated with ferrocene, which anyone that works with ferrocene would have done, is the lithiation thereof. So you can lithiate ferrocene. How do we lithiate something? Lithiation. It's a metallation reaction. We do a deprotonation and we lithiate it. But again, we have problems with selectivity. This reaction is done in the presence of tamida. What is tamida? Yes, it's a chelating ligand. Where did we encounter this guy before?
Carbide.
Yes, Schrock used it. So you did this reaction in the presence of tamida, but you end up with a question of stereo. Well, it's not selective. So that's a problem. But you can get around this by actually doing this reaction with tert butyl lithium. So that's N-butyl lithium, and then you get the monosubstituted product. Now that's great, because as a matter of fact, if you've got lithium here, of course, that gives you access to all sorts of beautiful chemistry. You can, for example, now attach all sorts of electrophiles there. So this is a nice starting material for chemistry of ferrocene. But notice that the chemistry is very similar, particularly in this example with the Fiedel-Crofts acylation, of the sort of reactions one would see with aromatic systems in organic chemistry. One final example, which I think is quite interesting, highlighting the reactivity of ferrocene, is its simple protonation. Now, let's looking at the molecular orbital diagram. Figure out, if I were to take ferrocene and react it with a source of H+, for example, HBF4, right? That's something that we typically use as a protonating agent to sort of titrate a proton, one proton into the complex. Where is that H going to go? Is it going to go sit on the CP? Is it going to go sit on the ion? What do you guys think? Yes? Yes. Yes. It's going to go sit on the ion. Why? Selective.
Like a hydride, like.
No, it's H+.
Oh,
So if we use HBF4, of course, it will be BF4 minus as the counter anion. Now the reason is that if you've got to look at the molecular orbital diagram, because where is that H going to attack? Which orbital? It's going to attack the LUMO. There's the LUMO. The LUMO, tell me about the LUMO. The LUMO, is it more metal-centered or is it more ligand-centered? Well, it's interacting, look at the energies, right? It's pretty close in energy, if you will, to these d orbitals here. It is more of a metal-centered orbital. And that's why the H+ goes for the metal. Yes.
H+ doesn't have electrons, right? So how can that be?
Well, you can think of it as an electrophilic attack.
Yeah, but shouldn't then it affect the HOMO? Because there are no electrons in the room. I don't know if it makes any sense. But you get what I mean?
Well, I mean, okay, that's another way of looking at it. You can think of the HOMO, which is the A1G attacking the, it could attack the electrophilic H+, but the thing is that's going to create another molecular orbital, and that will be this one here.
Oh, okay.
So, yes. That's not too important. I mean, I think the important thing to realize with ferrocene essentially is that its reactivity really is very similar to that of aromatic organic chemistry, and that is really because of these electrons, to realize that it's a sigma and a pi donor, a delta acceptor, and to understand the bonding interaction between a metal and CPs. Yes.
So if I were to change the symmetry so it wasn't d5d anymore, and therefore we change the molecular orbital diagram, would the hydrogen then potentially attack the ligand instead?
Oh, that's a very good question, Connor. I mean, you guys are really starting to think. The orbitals would change energy slightly, but overall it would stay more or less in the same order. I mean, if you actually go through the mental gymnastics of holding up the MO diagram, you won't see many differences, so it stays pretty much the same. And in fact, that's one of the reasons why the ring rotates freely in solution, because the energy barrier is very low, because there aren't considerable changes, energy requirements in changing the bonding situation. Of course it changes, but not considerably. So in fact, it's pretty fluxional. Now, just one final thing, I just want to remind you that today we've pretty much centered our discussion on cyclopentadiene. Remember, there's a plethora of others. Pentaphenyl cyclopentadiene, tetraphenyl cyclopentadiene, tris-isopropyl bisphenyl cyclopentadiene. You even have cyclopentadienes called super bulky cyclopentadienes. In fact, I've worked with them personally when I was a graduate student at the University of Cape Town. This was my master's thesis, was making these. Look at that. Oh my God. With mesotyl groups attached. These are extremely bulky, and you make these. Why would you make something so bulky? What's bulk good for?
To block off
Yes. To block off things, and to protect things. So you use these big ligands to protect very reactive metals. And there's a guy called Schurthader, who I worked with, who's now a professor at Erlangen, and he was doing a sabbatical then. We made some of these, and we made some chromium complexes. And he used them later on to make very reactive calcium and magnesium sandwich compounds. This was around 2006. So yeah, there's a huge variety of these. Interesting, with these pentaphenyl variants, they're not nearly as reactive as the C5H5. In other words, if you do a deprotonation and make this, so I've written it in that form already. So let's say sodium plus minus. That thing you can make it, but it's pretty stable. It's very stable actually. I mean, if you leave it in air, it's going to die. But it's not like sodium CP, which just like immediately, turns red and dies instantly. This is kind of pretty stable. Why would it be stable? Why is this more stable than sodium CP? Why?
resonance.
Yes, more delocalization, very good. We've got these aromatic rings here, so the negative charge is smeared out all over the place. All these resonance structures. Now actually, that's again a sort of a deceptively simple explanation, because actually, if you look at the structure of these rings are puckered in a propeller-like configuration. So delocalization is very difficult, but there is some marginal delocalization, but also, of course, the steric kinetic protection arguments as well, right? That you have these big substituents, and that protects basically the whole thing from decomposition. So next week, we're going to move on to clusters, isolobal theory, and the Waite-Ringos rule. So next week is going to be another, tough week of really lots of new principles.